Hello and welcome to MATLAB programming for numerical computations. We are in week number 7. In module 7, we are covering ordinary differential equations initial value problem. We are in lecture 7.5. This is the last lecture of this module. In this lecture, we are going to present some error analysis of Runge-Kutta methods. So far, we have covered Eulers method, which can be considered to be first order Runge-Kutta method. We have covered a couple of RK2 methods, specifically Eulers method and midpoint method. And in the previous lecture, lecture 7.4, we have covered RK4 method, the standard RK4 method. Today, we are going to present error analysis of RK methods. Okay. So first, let us talk about the local truncation error. We won't demonstrate this in today's lecture. What I will show you is with the global truncation error. Now, if we were to compare global truncation error instead of local truncation error, all of the ODE's solvers, they drop the overall order of accuracy by 1 power of h. What that means is Euler's method, the global truncation error is h to the power 1, Eulers is h to the power 2, RK4 is h to the power 4. Today's lecture, this is what we are going to demonstrate and compare. We are going to see how the error of Euler's method compares with that of Eulers method and RK4 method. Specifically, we are talking about the global truncation error. Let's now go to MATLAB in order to do this. Okay. What we will do is we will bring up the codes that we had written earlier. We had written RK2 Eulers method code, RK4 standard method code, and Euler's explicit method code. Okay, so RK2 Eulers method, which uses myFun, which we had done in lecture 7.4, and this was the function myFun. Okay. And then we had the RK4 standard method, okay, which also use myFun. What I will do also is open Euler's explicit method. Okay, so this was the Euler's explicit method, RK2 and RK4 methods. Euler's explicit method also, we are going to change this. Instead of minus 2t multiplied by y, I am going to use myFun of ti comma yi. Okay, exactly in the same way as we had done before, as we had done over here. That's what we have done again with our Euler's explicit method. Okay. Save this, okay, and what we will do is we will do a comparison of Euler's explicit, RK2 Eulers and RK4 standard method. Edit, compare ODEs. Compare global truncation error of Euler, Eulers and RK4 methods. Okay, what I will do is I will copy this part. T0 is 0, Y0 is 1. Let us take T end equal to, let's say, 1 also. H we are going to keep varying. So H all, let's say, is 0.1, 0.05, 0.01 and 0.005. Let's say these are the 4 H values that we have. for I equal to 1 to 4, H equal to H all I, N equal to what we had earlier, T end minus T0 divided by H. Okay, with this we are going to call Eulers explicit, RK2 Eulers and RK4 standard. Okay. So what we are going to do is we will call the RK Eulers and Eulers method, but we don't require everything. We only require the Y end at T end. So Y end my Euler, okay, and we are going to call it with our Y0, T0, H and N. Okay, so Y Euler is this, Y un equal to my un Y0, T0, H N, and Y RK4 equal to my RK4 Y0, T0, H comma N. Okay, so let's go to Euler's explicit and convert this into a function. Remember what we had said in module 1 when we discussed functions versus scripts. Scripts are something that we are going to use in order to complete a particular task in MATLAB. We are going to use functions if we want to compute something as a function of certain input variables, or if we want to repeat a particular task multiple number of times using the parameters. That is why we are going to convert all of these three ODE solvers, our Eulers method, Eulers method and RK4 standard method, into corresponding functions. Okay, the first function is my Euler. Okay, function y end equal to my Euler compare ODEs, my Euler y0, t0, h and n. y0, t0, h and n. So we don't need t0, we don't need y0, we don't need t end, don't need h, and we don't need n. So everything that was in problem definition we did not need. Why? Because the problem definition was given in the compare ODEs script. So there's just one script, which is the compare ODE script. My Euler, my RK2 and my un and my RK4 are going to be three functions. Okay, we will need to calculate t end also. So t end is going to be t0 plus n multiplied by h. Okay, so that is something that we have added. Okay, we do not want plot or anything of that sort. We want y end is nothing but y end, and that's the only thing that we need to do. Okay, likewise we are going to do the same thing with RK2 Eulers and RK4 standard as well. Before doing that, let's go to compare ODEs and see whether this works or not. And ERR 1 comma I equal to y Euler minus ABS, y Euler minus y true, and the true value, which I will again put it over here, y true equal to exp minus e end square. Okay, so let's just run this and see whether this works or not. Okay, we do get certain error. Y true is undefined. Let's go and see why we are getting that. Y true. Okay, that's again, it's the matter of MATLAB being case sensitive, and I was not careful about the cases. I need to initialize ERR equal to zeros 3, 4. 3 methods, and we have our 4 errors. Okay, so let's save and run this. Okay. So now we have our errors. The first row is the errors in Eulers method. So let's look at ERR. We only focus on row number 1, and these are the errors in Eulers method. So let's actually have h all up to 0.001 as well. Okay, and let us now do this for un and rk4, and likewise error 2, I is for un, yun and rk4. Okay, I will quickly go to rk2 un and save as my un. Okay, we remove this part and replace it with y_end function y_end equal to my un. Let's just copy paste this. Okay, and rk4 standard also save as my rk4. Okay, function y_end equal to my rk4, and just paste this over here and delete this part. Okay, again from my Euler we will take this t_end and paste it in both of these functions. Okay, remember that's what we had done earlier. Okay, now the next task is going to be to delete the output part and save this, and likewise this also we will do the same thing. Okay, so what we have done is we have converted I have gone carefully over how to convert explicit Euler into my Euler, a script which was explicit Euler we have converted into a function that was my Euler. The function takes the initial conditions, step size and number of steps, and returns the value at the end point. That's what all the 3 functions are intending to do. Okay, we use all of these functions in our compare ODEs file and run it for different values of age from 10 to the power minus 1 to 10 to the power minus 3. And we also plot for comparison. And what we are going to do is we will plot logarithm of age against logarithm of ERR. Okay, and let's run this. We have certain error. Okay, I think it should be plot of h all and plot of log of h all and log of ER. Okay, so these are the three plots. This one is for RK1 or Eulers method. This one is for RK2 method. This one is for RK4 method. All of these are straight lines. So the way we are going to compute the slopes are LE equal to log of ERR and LH equal to log of H, or sorry, log of H all. Okay, so our denominator is always going to be LH end minus LH1. Okay, our numerator is going to be LE all the rows last column minus LE all the rows first column. Our slopes is going to be numerator divided by denominator. Okay, so the slope for RK2 method, slope for Eulers method is 1.0, slope for RK2 method is 2.0 approximately, and the slope for RK4 method is 4.0. So this demonstrates the order of accuracy of the three RK methods from a global truncation error perspective. So we have the three straight lines with slope of 1, slope of 2 and slope of 4. Okay, so this was the discussion about global truncation error. Local truncation error is one order greater accurate than the global truncation error, just like what we had seen earlier in numerical integration. The global truncation error of RK2 method gives us the method as h to the power 2 accurate. RK4 method is h to the power 4 accurate. What you can do as an assignment is you take the previous example and demonstrate it with the midpoint rule and see for yourself that, like the Eulers method, midpoint rule also gives us order of h square accurate global truncation error. With that, I come to the end of this lecture and indeed to the end of module 7. In module 7, we considered ODE, initial value problem. We first started with Eulers method, considered both explicit and implicit Eulers method. Later, we said that in this module, we are going to focus on explicit methods only. In lecture 7.2, we introduced ourselves to Rangekutta second order method and extended it to Rangekutta fourth order method in lecture 7.4. In today's lecture, lecture 7.5, we did an error analysis of all the three methods. In lecture 7.4, we covered ODE 45, which is the most popular algorithm that is provided by MATLAB in order to solve the ODE problem. With that, I come to the end of this module. I will see you in module 8. Thank you and bye.